Hello again, everyone! Glad to see you all. Today we're going to explore a rather extensive topic on AI technologies. You know, I grew up reading classic science fiction, and one of my favorite authors has always been Isaac Asimov with his concept of the 3 laws of robotics. These ideas, created in the mid-20th century, are still relevant today and in many ways anticipated current discussions about AI ethics. So today we'll examine modern technologies through this lens. It's important to note that in this lecture, we're only introducing the variety of AI technologies. My goal today is to show you the big picture, what technologies exist and how they work at a basic level. If you don't remember all the details right away, that's absolutely fine. In subsequent lectures, we'll dive deeper into each of these technologies and look at their practical applications in testing. Let's get started. For those unfamiliar with the concept of the 3 laws, this is a set of rules that all of Asimov's robots must follow. The first law forbids a robot from harming a human, the second law requires robots to obey human orders, as long as they don't conflict with the first law, and the third law instructs a robot to protect its own existence, as long as this doesn't conflict with the first 2 laws. What's interesting is that even while following these seemingly simple rules, Asimov's robots demonstrate completely different decision-making approaches and ways of responding to situations. When we talk about artificial intelligence technologies, we're referring to a wide range of approaches to creating systems that mimic human intelligence. And I find it particularly interesting that many of these approaches can be seen in the different ways robots think in science fiction. Let's look at the main AI technologies used in modern systems. They can be divided into several key groups. First, there's fuzzy logic. Imagine a robot that evaluates the degree of danger to a human not simply as dangerous or safe, but on a scale: slightly dangerous, moderately dangerous, very dangerous. This is fuzzy logic, an approach where variables can take any value in a range from 0 to 1, not just extreme values. If conventional logic is a world of black and white, fuzzy logic adds all shades of gray. For example, in a climate control system with fuzzy logic, the air conditioner doesn't simply turn on or off at a certain temperature, but gradually increases or decreases cooling power depending on how hot it is in the room. This makes the system more fluid and natural, as if it were controlled by a human. Next are search algorithms. Imagine a robot needs to find the optimal route to evacuate people from a building. It systematically analyzes all possible paths, assessing their safety and efficiency. These are search algorithms. They methodically explore the space of possible solutions to find the best one. Search algorithms come in different types. For example, the BFS breadth-first search algorithm explores all possible solutions at the current level before moving deeper, and DFS depth-first search follows one path to the end before returning to try another. In real life, these algorithms are used in navigation system, robot planning, and even in computer games to determine character movement. The third group is reasoning techniques. These are particularly well illustrated by how robots might interpret the 3 laws differently. Let's look at 4 main techniques. Rule engines are like a direct implementation of the 3 laws in a robot's brain. Such a robot strictly follows given if-then rules, making decisions based on them. If an action may harm a human, then do not perform that action. Rule systems are widely used in business logic where rules are clearly defined. For example, in a banking system for credit approval. If credit score is above 700 and monthly income exceeds 50,000, then approve credit. The advantage of such systems is their transparency and explainability, but they can become very complex with a large number of rules and exceptions. Deductive classifiers. Imagine a detective robot that analyzes a situation and logically determines which actions comply with the 3 laws. Such systems draw conclusions based on logical analysis of available information. Deductive classifiers use logical reasoning to classify new data based on established patterns. For example, in medical diagnostics, a system might reason: if a patient has high temperature and cough and sore throat, then it's probably the flu. These systems are especially useful when there's a clear logical structure in the domain. Case-based reasoning is like a robot that learns from past experience. Last time I encountered a similar situation, the right solution was X, so I'll choose X again now. This approach is actively used in decision support systems. Imagine a customer service where the system finds similar problems that were encountered before and suggests solutions that worked in those cases. The key point here is determining the degree of similarity between the current situation and past cases. With each new solved case, the system becomes smarter, expanding its knowledge base. And finally, procedural reasoning, an approach where a robot plans a sequence of actions to achieve a goal, constantly monitoring changes in the environment and adjusting its plan. Procedural reasoning systems are especially useful in dynamic environments where situations constantly change. They're used in autonomous robots, self-driving cars, and control systems. For example, a drone delivering a package. It plans a route, but constantly monitors weather conditions, battery charge, and other factors, adjusting the plan in real time. The fourth and perhaps most extensive group is machine learning techniques. Unlike classical robots with programmed rules, robots with machine learning extract patterns from data themselves. It's as if a robot doesn't just follow rigidly set 3 laws, but learns to interpret them by observing thousands of human-robot interaction situations. Machine learning methods include neural networks. These are structures inspired by the human brain. They consist of layers of interconnected neurons that process information. Imagine a robot's brain consisting of millions of small blocks, each processing a piece of information and passing results to other blocks. Neural networks are particularly effective for pattern recognition tasks such as image classification, speech recognition, and natural language processing. For example, when your phone recognizes faces in photos or when a voice assistant understands your commands. Most likely there's a neural network at work. Their strength is in the ability to detect complex, non-linear patterns in data, but they require large amounts of data for training and often work as a black box. It's difficult to understand why they make a particular decision. Bayesian models. These models use a probabilistic approach, constantly updating their beliefs based on new data. A robot with a Bayesian model of thinking constantly evaluates the probability of various scenarios and adjusts its actions accordingly. Bayesian models are based on Bayes' theorem, which allows updating the probabilities of hypotheses when receiving new data. They are widely used in spam filters, determining the probability that an email is spam based on the words in it, medical diagnostics, and recommendation systems. Their advantage is that they can work with uncertainty and provide not only a prediction, but also a level of confidence in it. Decision trees. These are models that make decisions by sequentially answering questions. A robot using a decision tree might reason like this: is there a threat to a human? If yes, how do I eliminate it? If no, have I received an order from a human? Decision trees create a hierarchical structure where each node represents a question about some attribute. Each branch is a possible answer, and the leaves are final decisions. They are used in diagnostic systems, customer classification, risk assessment. Their main advantage is simplicity of interpretation and clarity. You can easily trace why the system made a particular decision, which is especially important in areas such as medicine or finance. Continuing our overview of machine learning methods, random forest is an ensemble of decision trees working together. Imagine not one robot making a decision, but a whole group of robots voting for the best course of action in accordance with the 3 laws. Random forest builds multiple decision trees on different subsets of data and with different sets of features, and then combines their results to improve accuracy and stability. This method is widely used in the financial sector for credit risk assessment, in medicine for disease prediction, in ecology for forest condition analysis. It is more resistant to overfitting than a single decision tree and often gives more accurate results. Linear regression and logistic regression are methods for predicting numerical values or categories respectively. For example, a robot might use regression to predict how safe a particular action will be for a human. Linear regression models the relationship between input variables and a numerical output, assuming that this relationship is linear. It's used for predicting sales, real estate prices, population growth. Logistic regression, despite its name, is used for classification tasks, predicting the probability of belonging to a certain class. It's applied in medicine for predicting disease risk, in marketing for identifying potential customers, in security systems for fraud detection. Clustering algorithms. These methods group data by similar characteristics without prior training. Imagine robots organizing themselves into groups based on how they interpret the three laws without external instructions. Clustering algorithms find natural groups in data, combining similar objects and separating different ones. The most famous is k-means, which divides data into k-clusters. Clustering is used in customer segmentation, highlighting groups with similar behavior, or in image analysis, grouping pixels by color or texture. This is an unsupervised learning method, meaning it doesn't require pre-prepared data. We'll discuss what supervised and unsupervised learning are in subsequent lectures, but jumping ahead, yes, it's roughly what you're thinking. I'll give you a simple analogy for now, and we'll cover formal definitions later in the course. Imagine you have a very smart small child, and you have the option of either raising them yourself or leaving them, hoping they grow up somehow on their own. Of course, before leaving, you'll leave them a huge amount of food, hoping they'll somehow figure out what to do with it. And most likely, this child will survive. But they might not become the person you expected to see. They might find a dog, get attached to it and think it's their family. The child will never learn to speak, but will be strong, resilient, and learn to live by dog laws. Returning to our analogy, you are the teacher and the child is your AI model. And in this case, you can decide whether you want to explain to it how the world works. These would be supervised learning techniques, or you would just give it access to data and the model will search for patterns on how to survive in the world on its own. Meanwhile, we have more techniques to cover. Let's continue with them. Genetic algorithms, methods inspired by evolution, where solutions mutate and crossbreed to find the optimal one. It's as if robot programs gradually evolved, becoming better and better at interpreting the three laws. Genetic algorithms model the process of natural selection, where the best solutions survive and pass their characteristics to next generations. They are especially useful for optimization tasks with complex search spaces. They are applied in route optimization, car and aircraft design, and creating game strategies. Their advantage is that they can find unexpected creative solutions that a human might not consider. And finally, Support Vector Machine, or SVM, a method that finds the optimal boundary between different classes of data. A robot with this type of thinking could clearly separate safe and dangerous situations, determining when to intervene to protect a human. SVM works by finding a hyperplane that maximally separates classes in a multi-dimensional space. It's a powerful method for classification and regression tasks, especially effective when the number of features is large compared to the number of samples. SVM is used in text recognition, image classification, outlier detection, bioinformatics. Its strength is good generalization ability even on relatively small datasets. Now, let's highlight the key points. AI can be implemented using a wide range of technologies, from fuzzy logic to complex neural networks. Different types of tasks require different AI technologies. For example, pattern recognition often uses neural networks, while logical reasoning may rely on rule systems. AI systems often combine several technologies to achieve the desired result. Understanding the basic principles of each technology is critically important for effective testing of AI systems. Don't worry if this seems like too much information at once. In subsequent lectures, we'll return to each of these technologies and examine them in more detail, with a focus on testing. From a practical testing perspective, each AI technology has its own characteristics and requires specific approaches. Testing an AI system without understanding the technologies used in it is like trying to check if a robot follows the three laws without understanding how it interprets these laws. For example, when testing neural networks, it's especially important to check resilience to various input data, including edge cases and unexpected inputs. Neural networks can give surprisingly strange results with input data that differ substantially from what they were trained on. For rule-based systems, it's critically important to check all possible combinations of conditions and ensure there are no contradictions between rules. Sometimes two rules can conflict under certain conditions, leading to unpredictable system behavior. When testing Bayesian models, you need to pay attention to the initial probabilities and how the system updates them as new data arrives. Incorrect initial probabilities can lead to biased results. By the way, here's an interesting fact. Asimov's 3 laws of robotics, formulated in the 40s of the last century, are still discussed as ethical principles for real AI systems. In 2025, leading technology companies are using adapted versions of these laws when developing safe AI principles. I think this is an amazing example of how science fiction can be ahead of its time and shape our technological future. To sum up, artificial intelligence technologies are a diverse set of tools that allow creating systems capable of performing tasks that require human intelligence. From fuzzy logic to complex neural networks, each technology has its strengths and application areas. As next-generation QA professionals, we must understand the principles of how these technologies work to effectively identify their weaknesses and potential problems. And remember, unlike Asimov's robots, real AI systems don't have built-in laws protecting humanity. It's our job to test them so they are safe and useful. In the next lecture, we'll look at AI development frameworks. We'll learn what tools are used to create modern AI systems, as if we were looking into a laboratory where robots of the future are created and programmed. See you then!